Good, what? Good afternoon, of course. Good afternoon, everyone. So, inshallah, today we will conclude this part of our chapter. Which chapter we are in? Chapter what? 3. Good. And we talked so far about what exactly, just roughly? Again, what we said just now. We were talking about the models of the diode, and we want that. Why? Because? Why we are talking about models of the diode? To analyze the circuit. That's a very good question. That's the best answer. To analyze the circuit. So when we have a diode in the circuit, we know how to study that circuit. Yes or no? So we have to replace the diode with its model. Yes or no? Very good. So far we have studied that in which domain? The DC domain. Very good. So that's what we have done in this class. Yes or no? And we gave enough time, the best time actually, for the CBD model because it's the best. If you want, caviar meal with shawarma cost. That's the example we gave. Yes or no? And if you tell that to the Russians, they will love you because they are the most consumers of the caviar. It's actually over the world, but for rich people only. So don't dream too much about the caviar. So that's the thing that we studied last time. And we are going to study today the small signal model. Okay? Any questions so far? Alas, we are going to move. As I said before, every single series, have you been watching series in TVs? Yes or no? Series in Arabic is what? Musals. Musalsalat are very famous. So if you understand the story, you have to watch every single one. Yes or no? Same story for this course. I told you in the beginning. Yes or no? So it's like a chain. If one of them is missed, everything will be gone. So to understand the full story of this course, you have to understand every single episode. That's what we call it. Halaq. Very good. Alright, I hope that the story now is clear to everyone. Okay, good. Alright, that's what we are going to keep moving today. So, small signal model. So, to understand that, it's very simple. Having discussed instantaneous DC and AC, blah, 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 blah. So, now we are going to apply that to build the AC model of our diode. It's fun. It is really nice, but we have to go step by step. You can see steps in here. I'm not going to read that, but I will go with you on the steps that I have on the right side, on your right side. So, this is what do we have here? This equation represents what exactly? The what? Raise your hand. Yeah? Yeah, very good. Or the IV characteristic. So on this side is the current, as you said, but you have here the voltage of that. So this is the exponential model of our diode. Yes or no? The most accurate. So here the parameters, currents and voltage here of the diode. They can be either DC or instantaneous. But in AC we cannot do that, but we'll show you how in a second. But in any case, in the DC, if we put here so basically the input of that diode is actually what? The IV characteristic. That means the input is, what's the input of the diode? Is that voltage. Give me the voltage, give you the current. Yes or no? So the input is V and the output is the current. And that's why we call it IV characteristic. Yes or no? XY. Yes or no? Okay, very good, very good. So if we have in the input of that diode a DC voltage, so the output automatically has to be what? A DC current. That's it. So that's what it means in this step. Now, what if in our circuit the voltage is instantaneous? So it has a DC and an AC. Okay, in that case, so because the diode doesn't know that, it takes everything. Yes or no? Make sense? So in that case, in the input, we will have to take both the DC and the AC. Basically, we have to take the instantaneous. Yes or no? So in that equation, we have to replace this voltage, which is our input. Yes or no? With this instantaneous there, and then we have to find the current. In that case will be what? The instantaneous current, yes or no? Because if you give me instantaneous, I give you instantaneous. If you give me DC, I give you DC. Okay? The AC is something extra. That's what we are trying to find. Yes or no? Yes or no? Clear? Good. Alright, so we take that exponential model, and then we put in the input that instantaneous voltage. And in that case, we will try to find the AC current, that AC current, and from there, we can get the AC model of the diode. Very good. And that's basically what we are writing in here. So as you can see now, see this lower capital means what? Means what? Raise your hand means what? We will now know who is following us and who is dreaming. Yes or no? Yes, you? DC value? Okay, nice try. Good. You? The instantaneous. Why? What's that again?
It's combination from the upper and lower case.
Very good. So we have a lower letter and capital or upper subscript. It's okay to make mistake, you see? Now she will never forget that. So this is the total. Yes or no? The instantaneous. Lower, upper. We said that in last time. Please revise. Okay? In that case, we have the same thing here. Lower, upper. Yes or no? Very good. Everybody on the same page? Let's keep going. Let's keep going. All right. So if we take that and then we replace it in the equation of the IV characteristic of the diode, now we have to put the DC plus the AC. Yes or no? But here we have the same thing, the instantaneous. Of course, there's a time here. Why? Yes. Why? Because where's the time coming from? It's coming not from the DC component, it's coming from this. So here, this will have both the time dependence, which is the AC, and the DC, which is time independent. Yes or no? Clear? By all means, if there is any ambiguity or something, there is no stupid question. There's always stupid answer. So all questions are welcome. Okay? And by making a mistake, you learn the correct. Yes or no? If you make correct, who knows what's the exact correct? So correct answer is not very exciting. So make mistakes in my course. Now, having said that, now we play mathematics. So we have exponent of something plus something. So in that case, if we split them, it will be exponent of that something times exponent of the other thing. Yes or no? And that's what we did in here. Yes or no? So this is clear. Good. Now, looking at this parameter, you see here, this is constant, so there's nothing about that. But here we have a DC over constant. So the whole thing is what? It must be a DC nature. Yes or no? It's a DC. There's nothing fancy about that. So by definition, then in this case, this will be the DC current. And how to represent that? We represent the DC quantities by how? How do we represent the DC, say, voltage or current? Upper, very good. So you see here, upper, letter, upper, subscript. Here it is not, something holy or something. It's just an agreement, a convention. And this is what Professor Adel Sidra, suggested in his textbook, which we are using as a textbook of this course. Somebody else can have something else. So the idea is that we convince and we agree about certain notation, so that we use it and we understand what it is. Do you understand? That's it. So it's not something special or something. So now this is the DC current times this thing. That's it. So this is the instantaneous current. Clear? Good. So, do we know what's the AC current here? We can't. This is the instantaneous, yes or no? But it's equal to a DC times something. So still we have not reached what we want, yes or no? We want the AC current, sir. Now we call for help of mathematicians, yes or no? Mathematicians are helping us with functions that are nonlinear. Why? Because here we have a nonlinear function, yes or no? Wait a second here, there's some problems going on. Go back. All right. So here, this is a nonlinear function. Yes or no?
Yes.
So we need to do what? In order to get the, or to extract the AC current from this complex nonlinear function, we need to make this linear. And this process, what we call linearization. So it's something like curved, and you come and then make it linear. Yes or no? And this, thanks to the mathematicians, one of the greatest one was Mr. Maclaurin. This guy is a mathematician, a British mathematician. He worked in the 1700s. So how many centuries so far? 3 centuries ago. And he built what we call, actually not him alone, also by another guy, Taylor. They built what they call power series expansion, meaning that you can take any function, whatsoever that function is, linear, nonlinear, especially nonlinear, something complex, and you can expand it into a power, a series, a summation of series of power functions. Okay. Mr. Maclaurin developed that for x, small x, means at x close to 0. So close to x equal to 0, for example, because that's the function that we have, expand that one, or a function can be expanded like this exponential of x to 1 plus x square over 2 factor, you know this factorial, plus etc. etc. Okay. So this expansion is actually Maclaurin expansion. Euler, later on, he used that for complex x. Mr. Euler, I think, is German guy, German mathematician, great guy also. But here, in Maclaurin expansion, exponential of x can be expanded this way using this expansion. If you click, I will update the slides. Or if you go to Wikipedia, that's what where it takes you. You will understand further about this series. They are very beautiful ones, mathematical series, but nonetheless, if you want to go deeper. But nonetheless, we take only this, but only for x close to 0. Okay? So, and to verify this, make x is 0. If x is 0, all this goes to 0. Exponential of 0 is what? 1. So here we have only 1 plus all these zeros. So it's true, at least for 1, for x equal to 0. Well, thank you very much. We can trust him for now. Okay? Now, if x is close to 0, x squared will be what? Higher or lower? So it will be even closer to 0. Yes or no? And all these, they will become even closer to 0. Yes or no? So we can say that these, we can neglect them basically. Yes or no? Correct? So we'll have only, we can take this exponential of x equal almost to 1 plus x. Yes or no? Now from our previous equation, what's that? Oops, what's that? Yeah, so that's our x actually. We will take this as x, yes or no? So exponential of x is actually x is equal to Vd over Vt. So if we do that, basically, then we come to this equation, the exponential of x. So this is x squared over 2 factorial, etc., etc. We can neglect, as he said, this, assuming this is quite small. We'll come back to this. So this is the condition of that expansion. Do you understand? So that means if that condition is not true, that expansion is not true. Do you understand? So it's only with assuming that Vd over Vt is quite small. Very good. By doing that, we can replace the exponential of x, or Vd over Vt, by 1 plus x. Yes or no? Correct? Clear or no? Very good. So you see, from exponential Vd, which is Vd is the changing parameter, yes or no? We come to 1 plus Vd over Vt. So that's exactly linearization, you see? We replace the nonlinear function with what? With a linear. This is a linear, yeah? This is a line equation, yes or no? That's it. That's the linearization process. One of the best example where mathematics helps engineers. Very good. And we like the linear. Why? Because let's follow. We take that equation now, and now we can expand it, yes or no? So ID was ID times, so here we have ID times 1 plus Vd over Vt, yes or no? If we expand it, we get this equation, which is great in here, but that's not a big deal. Now, you can see that this is the DC, yes or no? So because this is instantaneous current is equal to a DC plus what? Plus an AC. So this is automatically what? The AC current. Yes or no? Very simple. Take notes. Don't count on anything but your notes. Excellent. That's what it is in here. Very good, very good, very good. Thank you very, very much. Now, you see this current now is equal to this, or this ID. Let me write it now. I like to write it. Okay, let's go and write. Okay, so now, let's go with this. So now, this is a DC or AC? Very good. So this AC is equal to what? Is equal to ID over what? VT times what? VD. I told you before, there is no voltage by itself. We are talking about delta V. So we have always a reference to. Do you understand? Very good. Our reference here is what exactly this voltage is referred to what? What's the reference of this voltage? Is your hand? Who knows the reference of this voltage VD? The one that I'm writing here. What's the reference? Where is that reference is? Who knows? In the diode. Which one? Which terminal? The cathode. Yeah. Speak up. Yeah. The cathode is the reference of this voltage. It's the reference to the cathode because that's the reference. You understand? That's where this equation was taken from. Referring to the cathode. The reference means what? The voltage of that diode with the reference, that means of the anode with reference to the cathode. Huh? Okay? Put that in mind. It's also a refreshment. Okay? Very good. Let's keep going. So, in here, this is basically, we finished the DC, yes or no? When we finish the DC, this is a constant value now. Huh? Yes or no? This is constant, DC. Halas, that's it. This is constant. We have a current here that is equal to a certain constant times a voltage. It's like what? Which rule is this? Ohm's law. Very good, very good. That's what it is, yes or no? So Ohm's law say what? It says that the current, whatever is that current, is equal to what? Voltage, or delta V actually, divided by what? R. Very good. So from these two equations, what is R? This is simple, yes or no? So R is equal to what? Yeah? No, no, I mean this. Okay, let's take this. Let me then reformulate. Huh? So here, delta V or V is almost pretty much the same, yes or no? Yes or no? We are talking, we are trying to get the value of R, yes or no? See here? So VD or delta V is the same thing. That means what? If we take it from here, this is this. Huh? So 1 over R is actually this, yes or no?
Yeah.
This is 1 over R, yes or no?
Yeah.
So let me then make it simple. Let me take this off. Okay. We write it in a nice way. Huh? Sometimes when we... So 1 over R is nothing but ID over what? Over VT, yes or no?
Yeah.
Clear, yes or no?
Yes.
Simple. Huh? Yes or no? That means this what you have here is nothing but the inverse of a resistance. Yes or no? Very good. So that means R, which we represent here by small r d like this, to say this is the resistance of the diode, small, yes or no? In the AC domain. That resistance is equal to what? Is the inverse of this, yes or no? So it will be VT over ID. That's a very important answer. That's what we have here. Yes or no? That's what we have here. So the diode in the AC domain looks like a resistance, variable resistance, yes or no? It's variable. Why is variable? Because this is constant, assuming temperature doesn't change, yes or no? Because of this. Depending on ID, RD will be. Yes or no? This is a variable resistance. And the control of that resistor is not your, it's the current. The DC current, yes or no? Clear? See why it's variable? Doesn't change with time, it changes with the value of the current in the DC. Yes or no? Clear? Well, so change the DC current and then How we change the DC current? By changing the DC voltage. Yes or no? So the DC voltage plays with the current, and the current plays with the resistance, the AC resistance of our resistor, of our diode. Yes or no? One more thing. If the current is high, that means we have a little bit of voltage more. So the resistance will be small. Yes or no? That's it. So the more the current, and actually the current in the forward, when we bypass the barrier, the current will go where? Over the roof. Yes or no? Very high. That's why the diode in the forward, the resistance, its resistance is very. In fact, idealistically, that resistance will become what? Zero. And that's the short circuit model. Yes or no? Got it? Clear? Nice? Thanks to the mathematicians? We thank them. Yes or no? They did a very good job. One more thing. The temperature also is there. Yes or no? So to make this resistance smaller, the temperature has to be high or low? Very good, very good. That's a very nice observation. Yes or no? So if we cool it down, or the diode is cooled down, its resistance becomes what? See how nice is that? So let's repeat. Huh? See, I like these questions. I don't understand. Repeat. That's it. That's it. On the face. Very good. Let's get back to this. We are playing with the equations here. Yes or no? To understand what's the resistance. How can we control? Yes or no? Vt is equal to what? You tell me.
Vt?
Vt. No one helps, huh? No cheating.
Volt for volt.
Very good. That you need to revise. Yes or no? Did you revise?
Well, I revised this. I forgot.
Come on. Okay. Vt is very important. You should not miss this. Let me repeat. Repeat. Vt. Who knows Vt? What is it? Let's help your friend here. Raise your hand. Vt. What is Vt? Don't talk. Still? Paper is still. Raise your hand. Who knows Vt? So that I know who is revising and who is not. Alhamdulillah. Majority are not revising, but raise your hand so that I know. Or I can check anyone. See, alhamdulillah, majority are dreaming. Yes or no? Saha, you. Don't talk. Yes, Vt. Yes?
I think Q over T.
Very good. K what?
Q over T over
No.
You mixed up, but that's fine. KT. Very good, very good, very good. Nice, nice try. I will write it in red so that you don't forget it. Red, you know red, huh? Red light, wake up. So it's KT over Q. UT is what? Temperature. Yes or no?
300
What do we call this?
volt.
Thermal what? Very good. Thermal. Are we going to forget that? You tell me, huh? What do you think? Are we going to forget that? Never again. Alhamdulillah. Very good. Excellent. So, if the temperature goes down, Vt goes down. In the extreme temperature, when T is equal to 0, Vt is equal to what? 0. Yes or no? It's true, huh? Put 0, we get 0. Yes or no? What comes in, comes out. Yes or no? Very good. Let's go here. So if Vt now becomes 0 when temperature is equal to 0, Rd is equal to what? Absolutely 0. Big 0. Yes or no? And that's one of the tajalliyat, one of the aspects of superconductivity. You know superconductivity? Some materials go extremely resistanceless. They have no resistance when temperature goes down to absolute 0. Yes or no? And there you have superconductor. That means the resistance is very big 0. And the diode is not exception. Yes or no? You like that? See, physics and electrical engineering, they goes together, huh? Physics help the electrical engineer, and the electrical engineer use that, and thank you very much, and we make something. And that's what it is in here. See, the beauty of science and engineering, they go where? With the hands of mathematicians to very nice party. And that's the party in here. The resistance of the diode is equal to Vt over ID. Bingo. Now, when the ID goes really low, when ID goes low, can somebody tell me? The diode currents go down. In which region? Raise your hand. I need to know who is doing what. Yes, the representative.
Maybe when we have open circuit.
Hey, when? Yeah, that's true. When we have open circuit or when we have low current. So when? Give me just when? Representative, huh? I will have to change my mind. Okay. Anyone knows when the current is low? Yeah, you. Yes, tell me. Yes, of course. You raise your hand, yes or no? So. مثلا في reverse bias. But if we are in the forward, we are here in the forward, yes or no? So far we are in the forward. Let's put that. So that's, thank you very much. But even in the reverse, if you have breakdown, the current will go very high. Let's keep only in the forward case. In the forward case, when the current will be low, can somebody tell me? Raise your hand. Alhamdulillah, majority are doing excellent. Watching the stars. Yes or no? Yes, Reem?
When the voltage is less than the front-end voltage.
Very good. When the voltage is below the threshold voltage. Yes or no? That's what we said. We said that the real diode, we are talking about the real here. Huh? When the voltage of the diode is below the threshold voltage or the cut-in voltage, the current is extremely low. Yes or no? And in that case, that current is low. If we plug it in here, the resistance will be what? Very high. Yes or no? So it's almost like open circuit. Still in the forward, but you know. Do you understand now? Nice, huh? Very good. All right. Thank you very much. Now, another, as I said, another mathematician, he said, okay, you can expand any function, in fact, at any point x0, which is here the input, by applying this formula, which is actually the general formula of Mr. Taylor, another great mathematician, who impacted a lot engineering with these formulas. So you can expand that exponential in any place, not only when x is close to 0. In x, whenever it is, in x equal x0. We apply this formula. Again, for further reading, go there. But we are not going to use this in our, we are still going to use the small signal model, and that's why we have to assume x equal to or close to 0. That's why we call it small signal model, because x is equal to what? In our model, x is equal to what, or represent what? Vd over Vt. Yes or no? That is our x. If you remember that, let's go back a little. Okay, I see we are dreaming here. Where's that? Back to this, as you can see, this is our x. Yes or no? Vd over Vt. Yes or no? This based on this. Yes or no? So this only applicable when x is close to 0. When this is close to 0, that means when Vd is very small compared to Vt. Yes or no? That's what it is, yeah? That's why we call it small signal. That means the AC voltage has to be smaller than the Vt. Vt how much? At room temperature? 20? 25 or 26. So our AC signal has to be smaller than that. So is it small or big? Small, yes or no? Less than 25 millivolt. 25 milliwatts is a joke, yes or no? Something that you don't even talk about it in electrical engineering. Usually, I mean, but there are some applications. Very good, very good. Why we are saying that? Because we have to keep this condition to apply this. Yes or no? هذا الشرط for that series expansion. For our linearization, this is the condition, is that Vd has to be small. Don't worry about this number. Here, just to make the approximation stronger and stronger. If Vd is less than Vt, our approximation means to have this is valid. But the smaller that ratio, the better our approximation. That means what? The mistake that we do in our calculation is very small. That's what it is. Clear? That's what it is. So if we keep Vd, the AC signal, less than 5 millivolts, this will become really strong. Yes or no? Our linearization will become really perfect in that case. Yes or no? So we have to be always, this has to be correct or verified that the AC signal must be always this. Our AC signal must be always very small compared to Vt. That means if we divide them, we are way, way far from 1, closer to 0. You understand? Cool? Clear? Any question? Do I need to repeat? Let's keep going. Let's keep going. There is a storm here. And when there's a storm, there's a problem. And where there's a problem, we are going to solve this problem. Okay? Clear? Who has the textbook? So raise your hand. Show me the textbook. Who has the textbook? One? Ah, you have part. That's good. Who has the textbook? No one.
I have.
One, two. Who else? Two out of how many? 42. Alhamdulillah. So, this is exactly small signal model. Yes or no? Sawa lela? Makes sense? Yes or no? Tell me if I'm wrong. 2 divided by 42 is equal to what? Let's count. 0.2. So we have to add 0. So 20 over what? Over 40. Still, we need another 0. Another 0. So, what else? 200 divided by 40. Let's say 42. 40. 20 divided by 4, that's 5. 0, 0, 5. That means what? 5%. Yes or no? Wow. That's exactly an AC small signal model. Yes or no? That's bad for the revision. And bad for this course. Yes or no? I told you to bring textbook. Alright, those who have it, go to this page please. The old edition, the new edition, just scroll back and forth until you find this problem. Number what? 3, or this example, 3.5. But the others, don't let them down. We copied it here. Yeah? But the others, they can find the solution there. That's the most accurate one. Well, that's the most detailed one. So we are not going to go in details in here, but we are going to follow it together. All right. So what do we have in here? So we have basically a diode in series with resistance. And why we want that? Why we have this? To limit that? The current. Very. So, he said here that the resistance here is about 10 kilo ohm. You see the unit, It's in red, If you miss the unit, you know the rest. Yes or no? That means you are wrong. I'm considering here to take half, but I take all the right to take the whole thing out, 0. Because in engineering, a number without a unit, either it does make sense that yes, it doesn't have a unit, or if it has a unit and didn't put it, that means you didn't understand that. So it's not something luxury or, it's a must in any engineering value, especially when it has a unit. Some quantities they don't. Okay, good? So we have the resistance of 10 kilo ohm in series with diode, okay, blah, blah, blah. The power supply V+, this guy, has a DC value of 10 volt. Clear? Very good. Over which is superimposed a 60 hertz sinusoid of 1 volt peak amplitude known as the supply volt. What does it mean here? Can somebody tell me, teach me here? Wait a second, raise your hand. Nobody. I'm talking only to Uri. Alright, Uri. Okay. Tell me. What's the AC voltage? Explain, try, make mistake. It's okay. If you are right, then we'll say thank you.
Do we have to calculate it from the one end?
What's the AC voltage from this? Where's the AC voltage? Tell me how much it is. 1? Then?
Oh, okay.
Oh, okay, that's what I'm looking for. Yeah, the okay one. Yeah, keep going.
The sine omega.
Sine what? Omega is equal to what? 2 pi times F. 60. Yes or no? That's it. See that O? That's the one. See? That's the O. Okay. That's the O. That's the O. Okay, let's keep going here. So what does it mean? That means this AC signal, let's draw it here. Okay. Which is V+. Yes or no? V+ is the power. The power line or the power voltage. So it's like this. So it's like this. Yes or no? It's DC, the average of that, yes or no? This is equal to what? 10? 10 volt, yes or no? Very good. Now, this AC is equal to what? V, V plus if you want, yes or no? Is equal to 1 volt because that's the peak, yes or no? That's the peak. That's the one. What is that? Hey, 1. So, sine, as she said, Kareem, thank you very much again. 2 pi. F is equal to what? 60 times 60 dot 60 hertz. If it was kilo, we'll write what? So it will be 60 times 10 power 3. That's 60,000. C. Yes or no? That's what it is. Because we said sinusoid written circuit. Sinusoid, yes or no? It's superimposed. That means it's on top of this DC. That's what it means superimposed. Okay? When I say something is superimposed on something, that is on top of that something. Okay? That's a language issue. خلاص, is it clear now? Very good. So, very good, very good, very good. So, understanding the problem is number one priority for any problem solving. Yes or no? If you don't understand, don't do it. That's it. It's gone. If you are dreaming, keep dreaming. But that's the way to go. To understand. So, what's the question now? Calculate VD. What's this VD? The DC voltage. Very good. Using what? Of course, we know that's iterative. Huh? And I will ask question to make sure that, yes, we do know. Yes or no? Huh? Did you revise the iterative? Yes?
Yes.
Yes, very good. Okay, okay. And then he gives me for that method, what we call this? He gives me a voltage and the current. What we call this? The gas point. The starting point of that iterative, because we need to start somewhere, yes or no? And this usually we get it from the data sheet of the diode, or manufacturer of the diode. So, very good. Of course, the answer is there, but who knows how to find that answer? How do we use iterative method to find VD? By the way, to find VD, this DC, what do we do? First thing is that what we said last class, we have to ignore all the AC signals. That means we short them. Yes or no? We have the AC only here. Yes or no? We short it. So now we have only 10 volts. Yes or no? And we are going to find this VD. Yes or no? The DC voltage. Yes or no? Now using iterative method, we do what? Can somebody tell me? Iterative method.
We use
You know? Well, let's give another chance. Huh? That's all. No. That's not iterative. Absolutely not. But let's try. Thank you. Yes, go ahead.
You assume if the diode is on or off.
No. Yes?
We use
It's okay to make mistake. It's okay. Go ahead.
V2 minus V1. This equation.
But before that, there's a step before that. Yes or no? What's the first step? Yeah, you on the side. You have to come somehow. Yeah. It's only there. Only the answers. Yeah. Go ahead. Huh? What's the starting point? What do I do first? What do we do first? Tell me. Step one is do this. Huh? The what? How I know the diode is going there? So what else? This is not the first step anyways, but that's fine. What's the next step? Hi. Anybody can tell me or tell us? Yes, representative?
We assume VD is not 0.7.
Very good. Why? Yeah, because it's given. Yes, that's the guess point. We start from the point that is guessed. The starting point are given by manufacturer. So assume at the beginning 0.7 here. Yes or no? This starting point. That's why we call it the guess point. The starting point. That's the starting point. Good. And then we calculate what? ID. Yes or no? Very good. Now we calculate the ID. And then what do we do? I think the wheel is moving now. Huh? So what's the next step? Can somebody tell me? Alhamdulillah. Go ahead.
I think calculate VD with the new current.
Very good. We calculate the VD with the new current and that equation. Of course, you have revised that for sure. Huh? Alhamdulillah. Very clear. So V2 minus V1 is equal to 2.3 VT. You know VT, right? Alhamdulillah. That's nice too. Okay, log base 10 of I2 over I1. Yes or no? So where is I1? Where is I2? Where is V1? Where is V2? So there is we have to go quickly. Yeah? So what's where is I2? What's I2 here in this equation? Which the new current? Who said that? Thank you. This is the new current I2. Yes or no? And I1 is out current. What is that? The one that we start. The 1 milliamp. That's the start one. Yes or no? Very good. And V1. Same thing, the previous one, that is 0.7 volt, and V2, the one that we need to calculate. And then what's the next step?
Compare the V2 to
The same. Yeah, we compare V2 to
V1.
to V1. Very good. And then?
If they're equal or precise to the third.
Yeah, to our precision. In our precision here, what's the precision of this number? Third. Very good. Or 10 minus 3 what? Volt. It's not digit. The third digit or 10 minus 3 volt. We can have the same thing for the current. Now look at the formula here just to give you some beauty of mathematics. When V2 is equal to V1, this is what? So, this cannot be 0. This cannot be 0. So the log must be 0. When the log must be 0? When I2 is equal to I1. That's what it is. So at the end of the day, when the currents doesn't change, the voltages doesn't change as well. See how beautiful mathematics is? Okay, good. So, and then we continue until we make sure that 0 is equal to 0 this side, to our precision. And then once we are done that, then we get the right VD and the right ID as well, yes or no? Very good, very good. And then we come here and use that information in RD, yes or no? RD is equal to what? VT over? Very good. So we use ID that we have here to calculate this RD in here. Excellent. Now, the question that comes next, calculate the amplitude of the sine wave signal observed across the diode here, yes or no? To find out how we find it? How do we find the sine wave? Of course, because we have sine wave here, there must be sine wave here, yes or no? صح ولا لا? And that basically is this sine wave, yes or no? Correct?
Yeah.
So how much is this? How do we find the sine wave here?
Apply nodal analysis.
Just a second. Yes? Go ahead.
Apply nodal analysis, like we saw.
Yeah, you tell me. If you apply that and you apply it here, how do you find it? It's straightforward, by the way. It's not big deal. It's very easy. Try.
Or mesh analysis.
There is no measure, really. It's
nodal
one
analysis.
single loop, very straightforward.
VD,
Try.
VD minus VS over R.
VD minus VS? Oh, no. That's not.
Will give me the current and then I will multiply by the R.
La. This is famous. We are looking at this voltage and you have this voltage, yes or no? Now in this AC analysis, remember that we took off all the DC values, yes or no? We have only AC, yes or no? Just a way of writing it only. It's the same circuit, but that we have only the AC here. This is the voltage of the AC, the input, which is this one. How do we find this? We know this one, yes or no? Is where this one, yes or no? This is that one, yes or no? That's VS. If you remember, this is nothing but VS in that circuit, yes or no? This one. This is that VS, yes or no? So VD here is the AC voltage across the diode, yes or no? That we represent now in the AC model by resistance, yes or no? Now that VD is equal to what? Anybody knows? Raise your hand. So let's count. Raise your hand. 6, 7, 8, 9 out of 42. That's how much ratio now? Where we are? 9 out of 42. 9 out of 42. That's 0 point. صح 90 over 40 almost 45 50% يعني صح no 9 over 40 20% close to 20% of the class alhamdulillah. Let's give it a shot. Go ahead. What's that? Very good. And from there how we get it? VD is equal to no VS by RD.
Divided by RD plus R.
Well, that's what it is. Remember now this? It's a voltage?
Divide the rule.
As simple as that. Very good. Excellent. So, I will write VD, the AC signal, is equal to VS, or actually this guy here, V plus AC, of course, times, I will write it in red, times what? Times RD divided by RD plus R. Yes or no? voltage divider, yes or no? But look here, RD, I will talk about that later. So the peak amplitude of the voltage across the diode would be the peak of this times this, yes or no? So this is 1, yes or no? Multiplied by this, divided by this and this. Yes or no? That's it. If you calculate it, that's what you find. That's the peak amplitude, 2.68 millivolt. Do the calculation. Is that acceptable? Why? Yeah, exactly. It's much smaller than VT. Yes or no? Because otherwise we cannot write RD like that. VT over ID. Yes or no? So our model is correct still. Yes or no? We can apply it. Yes or no? That's what it is. That's what it is. That's the condition. Less than 25 millivolt. Very good. All right. For further details, go to this page, please. Textbook. Okay. All right. That's what we said so far. We're not going to repeat that now. The next application of the diode, we did last time an application for diode, yes or no?
Yes.
What was that? Rectifier, thank you. Now the second application for diode is regulators. What do we mean by regulators? Regulate the voltage, meaning what? Anybody knows what means regulate the voltage? You heard this also about the news too. Control voltage, but almost there, almost. It's control for sure, but not completely. What does it mean here? Exactly, make it stable, make it constant. Boom. And that's one of the applications of the diode. So regulators means مثبتات. Like regulators of what? Of prices. If you go to the shopping, the shop will list some products, they say they are being fixed. So they are regulated. Who regulates them? The government. You understand? So the government said this is fixed price. Yes or no? So we say that the prices have been regulated. By whom? By the government. You understand? Doesn't matter who regulates. It matters that the price does not change. It's not an AC. Today is 5 dirhams, tomorrow is 100 dirhams. Who knows? But the government comes, this is the price and that's it. If you violate, you pay the fine. You understand? That's the same thing here. So here, and it's everywhere in the world actually, the voltage now is regulated, fixed, thanks to the diode. How? Says next slide, so let's go. Ooh, another storm. A storm means what? A problem. A problem means need solution. This page. Of course, how many percent we said? Small signal was what? 5%. Alhamdulillah. Better than nothing. 5%. The 5% people. Go to this page, please. All right, go. So here, what we mean by the voltage regulator, we read first the problem and see. Consider this circuit. A string of 3 diodes. We have 3 diodes on top of each other. Is used to provide a constant voltage of 2.1 volt. How come? How they can provide that voltage? Because what? Anybody? Yeah, because? Yeah, speak. He is serious. Here, so what? And then? Because the diode in the forward, yes, go ahead. At what? What's that 0.7? The voltage drop of the diode. Because the diode in the forward is like what? Battery. That's the point. Okay? It has to be conductive, of course. Yes or no? So, when it is, of course it's conductive because 10 volt is way above 0.7. Yes or no? If this was just, say, 2 volt, can these diodes work? They never work. Why? Because 2 here is less than enough. We need 2.1 and above. Yes or no? To make them conductive. It's not only forward, but they have to be conductive. That means it must have enough built-up voltage to make this conductive. That means 0.7 and above. You understand? So now we can replace the battery with the diode with the battery, and becomes 0.7, and the whole thing will become 2. Got it? This is the way you have to understand. Okay? Clear? Good. So I'm not going to finish this today, but you have to go to this textbook. So, but I'll give you the point here. Now the question is, what is the change in the regulated voltage caused by plus or minus 10% change in the supply voltage? This supply voltage, it changed by how much? By 10%. That means the variation will become plus or minus what? 1 volt. Yes or no? That's what it is. Good. So this is the AC and this is what? The DC. Ah? Very good. So because of the DC, it keeps this voltage at what? At 2.1 volt. Yes or no? This is a done deal. Now, when we apply the AC, we have to know how much is the AC. That's the variation, okay? That's what we need, what we mean by the change. That's the change. The change of the voltage here in the DC, the total voltage, is changed by the AC that happens here. Because we have here AC, we will have an AC. So we'll have to compare that AC to the DC. If it was too big, then it's not regulated. Yes or no? If the variation is very small, we can say that the voltage here, the total voltage, is almost constant. Yes or no? So we have to make sure to calculate this AC. So, to calculate this AC volt, what we did last time, what we did? We have to do what first? We have to. So that means the question is basically study this in the AC domain. But before AC domain, you have to study it in DC. To find what? To find the current. Yes or no? Do you understand? We need to find ID because we need ID in the AC. Yes or no? Very good. Clear? So we have to find first ID. Yes or no? We have to do the DC analysis first before the AC. We cannot do the AC before the DC. Yes or no? Because the DC analysis give me the current ID. Yes or no? Correct? Correct? Very good. So the current here is very simple. This voltage, DC voltage, 10 minus 2.1 divided by R. Yes or no? As simple as that. If you ask a iterative, he didn't ask iterative, so I can give him that ID. Bing. Yes or no? Once I get that ID, then each resistor, each diode will be replaced by a resistor. Yes or no? And that resistor is equal to what? RD is equal to? VT over ID. Because they share the same current. Yes or no? So these diodes, they will be represented by the same resistor. Yes or no? Each resistor will equal to VT over this ID. We just calculated it. Yes or no? And of course, you will find that RD here is very, very small compared to this voltage. Yes or no? We know that. This resistor, this is 1 kilo. Yes or no? This will be really, really small. Yes or no? Very good. Now, to calculate the AC voltage is again voltage divider. Yes or no? It will be this AC times this total resistance, which is 3RD. Yes or no? Divided by the total resistance plus this. Yes or no? Clear? That's it. When you do that, you find it really, really small, VS here. And again, you have to go to the textbook. Revision. Very good. Now, the second question is, if we put a resistor RL of 1 kilo ohm in here, how much does it change in here? Now, what do you think? Does it change or not? Why? So
So the voltage will be equal.
But yeah, still, it's half, but it's not the total. Yes, Ray. It's correct to some extent. Remember your answer, right? You will find the answer now.
It will change because the RL is going to be much bigger than the...
Exactly, and most of the current will continue flowing here. Yes or no? It's correct. So in parallel resistance, the current will go where? In the least resistance, in the smallest resistance. So this will not take much of the current in here, and therefore the voltage here will not change because the voltage divider here did not see any change, much of change in the current. Yes or no? Yes or no? RD stays the same. Yes or no? Because the current did not change much because the resistance still here is quite small compared to 1 kilo ohm. Yes or no? So two things makes the regulators. Two things. First is the constant voltage drop of the diode when it's conducting to give me a good DC voltage, and also thanks to its very small resistance to keep this current flowing only on that. So the voltage in DC in here will stay the same. Yes or no? Because now when this regulator will fail, is when this resistance becomes very comparable to this. Yes or no? Now, if there is a resistance here, instead of 1 kilo ohm, we put 1 ohm, for example. Now the current will see another current there, and will go, part of it will go there, yes or no? And therefore the current here will change, and if the current change in here, RD will do what? Will also change. So if this resistance is very small compared to this current, some of it will go there, this will decrease, the current IV decrease, RD will do what? Will increase. And if it does that, we come back here, if this now resistance increase, if this increase, if RD increase, now VD, I'll say, oh, wait a second. If RD increase, we cannot neglect it compared to R, and therefore VS here, the VD here, will be almost close to VS, yes or no, because this will get closer to 1, because RD becomes quite big, and VS that we have here will happen here, and therefore the voltage will not be regulated anymore. Yes or no? It will be out of the constant domain. And this is very nice. So these are the two features that makes the diode perfect to the regulators. Again, with the condition that the load here become small. And that's it for this course. And see you inshallah next week. Please make a revision. Any question? Well on time. See you next week.